Hello, everyone. Thanks for turning up nice and early. So I'm going to tell you a little bit in my lecture about rheology in the pocket theories workshop. There are some unfamiliar words there, which I shall explain later. But before I get on to my lecture, let me just thank the Society of Rheology for giving me the honor of being the recipient of this Bingham Medal. I must say, when I received the email from Anne and to say that I should call her, and then she said down the phone that you're giving me the Bingham Medal, I was embarrassed. That apparently is the embarrassed emoji. It's not embarrassed, it's a little bit embarrassed. So I said for me, because the point is, I'm not a rheologist. I said that in Houston when I gave a plenary lecture, and no one took any notice. So I'm going to say it again, I'm not a rheologist. And that is true because, as my students and postdocs will confirm, I've never knowingly done two things, either operated a rheolometer or written down a stress tensor. So that means that I'm not a rheologist. So this is kind of slightly embarrassing for me. And let me actually, in fact, tell you a secret. I've never confessed to this secret in public. But a while ago, in fact, in 1991, that's slightly earlier than that. But a while ago, I actually made myself this promise when I actually joined Peter Pusey to start the self-meta group in Edinburgh. I took one look in the rheology literature. I said, that's way too complicated. I'll never understand it. I will never do any. In fact, if I remember correctly, I made a pact with Peter Pusey that we won't touch rheology. So, that was back in 1991. But I didn't keep my promise to myself because I got frustrated at some point. And let me tell you just a little bit of personal history. I got frustrated because, as you will all know, just before Peter Pusey came to Edinburgh, he did these famous experiments where he showed that these PMMA, sterically stabilized PMMA colloids behave as Hart spheres. And what they do is that when you make a colloidal fluid with these Hart sphere particles, then at 49.4%, the fluid goes unstable. Any higher concentration, they crystallize. Now, the rheologists are not particularly interested in crystallization, but the rheologists are interested in the low shear viscosity. And we all know that the low shear viscosity, this is the relative viscosity at low shear, in other words, ratio to the solvent viscosity. It goes up with volume fraction. How it goes up at the beginning is well known. This is the Einstein term. This is the bachelor term. It took 70 years to do the bit in the middle, but never mind. So the question is, what happens next? Okay, so in particular, I was interested in what is the relative viscosity of the most concentrated possible Hart sphere fluid that is still thermodynamically stable. Okay. Now, as of 1995, the data in literature looks like that. Now, at around about 1995, that was when people were doing massive computer simulations, analytical calculations, trying to calculate this curve. Now, if the end point varies from 24 to 400, every theory is right. Every simulation is correct. It was indeed the state of the literature. So I was deeply frustrated by this and thought, well, let's do something about it. So that's how, in fact, I got into doing, at least doing the sort of baby rheology. There's no G prime, G double prime yet. This is only low shear viscosity. And in fact, I rapidly realized the reason why there was such a big spread was due to two things. One is the systems are not always Hart spheres. The most cited paper, this one, Papier and Krieger, they actually tell you that their system crystallized at 30%. That was before the Pusey and the Megan paper, so perhaps there was some reason for them not to know that that means they were not Hart spheres. Okay, but the other reason is that actually people don't always reach the low shear limit. So when you get to concentrated enough, you have to get to quite low shear to get to the north bit, the low shear bit. Okay, so what I did was I used a Zim viscometer. So Zim viscometer is an object that has a test tube floating inside another test tube. So my one actually was a gift from Dave Waits. Okay, I visited Dave when he was still at Exxon. He happened to have 3 and he gave me 1. I very carefully carried it back from the transatlantic flight and it wasn't broken. And Andy Schofield kindly looked this up for me a few months ago and it was covered in dust, but it's still there. So here, the inner tube is in fact the stator. I've taken the most inside rotor tube out. The outer jacket is a water jacket to keep the temperature constant. Okay, so what you do is in the inner tube, you fix an aluminum disc, you rotate a magnet on the outside to give a rotating magnetic field. The eddy current induces this disc to turn and it drags the inner tube. The point about this, the point about this is that this was first made by Zim. The reason for mentioning that is that Zim was himself a Bingham medalist. Before I was born, I think, let's say 1960, that's before I was born. But this was first made by a later Bingham medalist, to reach very low shear rates, amongst other things. Okay, so you can turn the magnet practically infinitely slowly, and practically the only extraneous friction is from the bottom and from the little meniscus here. So you can reach very low shear rates. So we did the measurements. These were our results. And the number we found was about 50. And of course, 50 is bang in the middle of this whole range. So, you know, I mean, almost experiment I did would have been bound to be right in that range. Now, it would be fair to say when we first published that paper, in fact, one of the referees actually said, and the report didn't quite say this, but it basically says, Poon, never heard of him. He must be wrong, because everybody knows he's 24. So I wrote there and said, well, you may not have heard of Poon, but Poon may still be right. And 50 is bang in the middle of the range. So, so basically, I think no one believed us to start with. And then some very famous people, we did the experiment using a Zinn viscometer. This time they made it themselves. So, I mean, this is Bill Russell, who is another Bingham medalist a few years later. So if a Bingham medalist checked it, and he concluded that pH assay data, they did it with pH assay stabilized PMMA as well, and they concluded at the end of their paper, all right, they're right. Okay, so thank you, Bill. And in fact, Paul Chaikin later became a collaborator as well. So these Princeton people repeated the experiment. They found 50. We found 53. We split the difference, but it's 50. Okay, so that was how I got into rheology. So, you know, when I look back at this and I thought, well, you know, if I use a piece of apparatus by previous Bingham medalists and another one said I was right, maybe it's okay. But of course, I didn't do it. The work was done by Steve Meeker, who's a very gifted student and postdoc. And since then, in fact, when I look back, of course, all the rheometer bits were done by these people, all the stress tensions were written down by these people. And in fact, it turns out that this list includes some of my very best students and postdocs. So, you know, thank you if you're in the audience. I don't know whether any of these people are attending. I know the Edinburgh people are now still in Edinburgh, but if one of you are in the audience, thank you very much. But also, of course, I have a whole bunch of senior collaborators, which includes a whole number of previous Bingham medalists as well. So I decided I won't be embarrassed if all of you think that actually the name here is not mine, but they're all of these people. So if we can do some micro action, all of these names should be on there. So, you know, just let me say in public that I'm accepting this medal on all of their behalf. Without them, I couldn't have done it. Okay, so let me then give you an apology. I should be here, presumably somewhere in there rather than here, but I should be here. Unfortunately, due to a whole bunch of personal reasons, some good, some not so good, I couldn't be there, so this is where I am. It doesn't quite look like that at the moment. It's pouring with rain as I record this, but do come and visit us someday. But I'm sorry I can't be with you. That's the way things have turned out. But I would rather be with you, but I can't. So, you know, when I knew that I had to give this lecture, I started thinking, what should I tell you? I mean, typically, Bingham medalists would give a lecture explaining their recent work, which is, you know, a lot of high-power rheology. I already told you I'm not a rheologist. I haven't got very much high-power rheology to tell you. And indeed, the other trouble is, I gave a plenary lecture in Houston. This is the best bit of the Houston meeting, the beer taste. Fantastic. Look at the size of the whole. Anyway, so at Houston, I gave a plenary lecture on non-Brownian suspension rheology, which is to do with how friction and particle contact have now been brought into suspension rheology. The subject is still ongoing. I could tell you about that, but you know, the trouble is with the pandemic in the middle, 2018 just felt like last year. So it's 2 or 3 years that I cancelled in my brain. So I had a feeling that I'd already given this talk to basically this audience. So I decided I don't want to bore myself, so I'm not going to give that talk. I'm not going to tell you about what has happened to suspension rheology since. Instead, since you're all here and got up early for this, let's have some fun. I'm going to take you into the wild west of rheology and give you something that is kind of bit out of the way, bit unexpected. I hope this is at least some fun, and if you think there's something interesting in it that would help you to think about the future of rheology, so much the better. So let me take you to the wild west of rheology. And the way I'm going to do that is by one of the early pioneers of the subject. And this, you may not know who this is. This is Scott Blair. This is a double barrel name. Scott Blair was one of the earliest rheologists, and indeed, if you go back, so this book, A Survey of General and Applied Rheology, was published first in 1943. This is the second edition in 1949. And in fact, if you look back at Bingham's own history of the Society of Rheology, you find that he tells you that Scott Blair was one of the British people who were there in the inaugural meeting. So he was one of the original rheologists. If anyone knows what medal he's wearing, Gareth McKinley would know. I presume Gareth's in the audience. Please tell me. I nicked this photo from Gareth's own Bingham lecture. I would like to know what medal he was wearing. But anyway, so he was one of the pioneering rheologists, and he wrote a book summarizing results obtained basically 20 years after the Society of Rheology was founded. This is a survey of general and applied rheology. It's not a very thick book, it's about a centimeter thick, slightly bigger than a pocket-sized penguin book. So in fact, Scott Blair's work has featured once already in a previous Bingham lecture, because Gareth actually talked about Scott Blair's so-called frictional calculus of soft materials with parallel rheology. The slides are available on the Society of Rheology website. Do have a look at it. But I'm also going to be inspired by Bingham's book in my lecture, because if you look at what chapter is it, chapter 16, you'll find that the word there is psychophysics. Psychophysics is the subject that relates psychology to rheology. So in other words, how do I relate what happens in the rheometer to what happens either in my mouth or on my skin? Okay, so in fact, one of the pioneering rheologists was also a pioneer in starting the subject of psychorheology. And in fact, he was driven to invent his fractional calculus to do equations of to do flow equations, because he wanted to do psychophysics. Okay, so let me just show you the next page just for scaring you. If you read the next page, he mentioned a paper published in 1923 about the American Psychological Association. He said, we asked a number of blindfolded subjects to dip their fingers into various liquids. I don't know if you can see it. Let me magnify it for you. You see that table? This is a particularly good line. Apparently at 10 degrees, if you dip your fingers into mercury blindfolded, you think it's mud. Such experiments presumably will not be allowed anymore. That's kind of interesting. Those were kind of gentler days, maybe. Anyway, so not all psychophysics is equally dangerous, but I just want to point out to you that Scott Blair, one of the pioneering rheologists, was in fact a pioneer in psychophysics as well. Now, the subject can be called all kinds of names, but Scott Blair was inspired originally by Bacon. So in fact, it turned out that he worked at the Rothamsted's experimental station, which is a British research station on food, and he worked on doughs. And he said a few years after he started, he said, look, I found out a lot about the dough. He was doing rheology on dough. He said the frustrating thing is I haven't found out a lot about the bake. So in other words, he discovered he didn't know how to relate what his rheometers, his early rheometers were telling him, and what the Bacon was telling him, because Bacon used words like this. These are modern Bacon's words, but presumably evolved out of an early Bacon vocabulary. They use words like extensibility, elasticity, tenacity, stickiness. What does that mean? How do you translate Bacon's talk, what Bacon's fingers are telling him or her, with what's happening in his rheometer? Fortunately for him, he was married to a psychologist, and he also found that there was a refugee from Nazi Germany who was a psychology professor living a few doors down from him without a job. The next thing he knew, he was busily inventing psychorheology. Excuse me. He was busily inventing psychorheology in his Bacon research. And in fact, so he wanted to relate what the baker's fingers are feeling to what he was measuring on his rheometers. So in fact, he articulated his first research question, which was, what were the smallest differences, thresholds, in the viscosity of pure fluids and the elasticity of solids, which could be detected with known certainty? So in other words, if you make, say, two doughs that are slightly different, say with slightly different G prime, for example, what is the smallest difference that the baker's fingers would detect? It's undoubtedly a psychorheological question. If you need to do some rheological measurements, you need to do some measurements with the subject. Okay? I mean, he did more than that, but that was turned out to be his first publication dealt with this question, which was in the Proceedings of Royal Society B, published in, when was this? 1939. So, as I said, the subject could be called psychorheology, psychophysics, entropy physics, but eventually the journal that was actually published to deal with such work was called Journal of Texture Studies. So while this now says the Journal for Food Oral Processing Research, in other words, psychorheology of food, if you read the early issues of the journal, it was not just focused on food. in 1969 when the journal was first founded. You read the blurb on earlier websites of the journal. It says this is about texture of all kinds of gooey stuff. It could include skin formulations. But nowadays the journal is focusing too. Of course, this was far, far, far later than the Journal of Rheology, 1929. But insofar as, rheology is in fact about, this is not the terminology that rheology is typically used, perhaps, but it's about tactile or mechanical texture. There ought to be a bridge between these two fields. And that's the bridge that I'm trying to take you. I mean, this is the Wild West bit. It's not perhaps an average subject for Society of Rheology conferences, but let me take you there and see whether there's anything interesting there to do. So I'm going to talk about rheology in apothecaries workshop. In other words, in America, I think we call them druggists. In Britain, we call them chemists. So in the nature of transatlantic cooperation, I'll use neither word. I'm going to use apothecaries. Okay. So I mean, a lot of apothecaries use the mortar and pestle as their symbol. And by the way, RX, the R with this crossed out, crossing our bit of a word is a standard method for indicating an abbreviation. In fact, this is an abbreviation for recipe, which is a Latin word for take thou. Singular you take. So in other words, it's meaning of a recipe. Take a pound of mustard, grind it up, whatever. So this is the beginning of all recipes, whether for cooking or for making drugs. So that's the apothecary symbol. So what I'm going to try to show you, the kind of real Wild West fun bit, let me do some rheological history with you. Let me show you that, in fact, I want to make a case that all these early modern apothecaries, by early modern, I mean sort of Renaissance period, 16th century, that these early modern apothecaries were actually perhaps the first rheologists. We should retrospectively give them all membership of the Society of Rheology. Present them with a bill for membership with interest. But the other thing I want to show you, which is perhaps slightly a more conventional rheology talk, is my own first encounter with psychorheology, which was in fact a piece of work triggered by the COVID pandemic. So this bit is just pure, good, clean fun, no equations. This bit, I can't remember whether there are any equations, but there may be. But this bit is slightly more conventional rheology talk. Okay, so let me take you to Renaissance apothecaries. This work was is still funded by the Royal Society in the UK. So this was in fact part of a project that I'm doing with an art historian in Edinburgh and in collaboration with my postdoc James Richards on early modern cosmetics. Okay, so if you ask me why I'm working on early modern cosmetics with Gilbert and the questions I can tell, and also the original title of the talk that I wanted to use, but I was banned by the organizers. It was too rude or too explicit. But you can ask me, I think. Okay, so in fact, Jill's interest was in reading early modern recipe books for ladies to make cosmetics in their own kitchen. Okay, so her specialty was Italian cosmetics recipe books. Okay, so in particular, the one she was reading was this book, Ornamenti delle Donne, which is Women's Ornaments by Marinello, which was first published in 1574 in Venice. So this is the last quarter of the 16th century. This is a title page of one copy. So here's a standard recipe, just gives you a feel for the sort of things that we are working on. So take a pound of mutton fat, wash 9 times in cold water, mix it with the foam of an egg in, the mortar and pestle, and with a little butter, then add powdered mastic and frankincense and apply several times. Jill actually tried this in her kitchen using cocoa butter. She also tried it with mutton later. It won't only improve wrinkles on the forehead, but also those of the face and those of the stomach made by parents. I leave you to test it out yourself, but Jill said it actually felt rather nice when she tried it out in her kitchen using both cocoa butter and lard. And I'm sure James is looking forward in the rheology lab to buy some mutton fat. That's the way to monopolize rheometers, because it smells so bad that no one will ever come near the rheology lab for months. Anyway, so in fact, I mean, those of you who know about these things would actually recognize this is actually a recipe for making a high internal phase emulsion. Mutton fat gives you the fatty bit. You wash it and then almost totally dry it. Then that introduces a tiny amount of water, but only a very tiny amount. You heat it up with egg white, foam of egg white, denatured egg proteins is a surfactant that coats it. I don't know what the butter does. This is just a fragrance. Okay, you beat it up, you get a hype. Of course, we still make skin cream that way, and it apparently works. And if you do the rheology, this thing has a huge stress. is maybe perhaps not quite a Bingham fluid, but certainly would fit Herschel boundary. Okay, so that's the sort of thing that we're doing in this project. But doing this project actually led us to begin to actually think about how the early modern apothecaries actually classified their materials. So look, skin cream and these kinds of recipes that we study are all goo. Okay, and goo is of course the subject of salt metaphysics, and you all know that salt metaphysics goo is about materials with interesting mechanical texture. That's why salt metaphysics and rheology are like that. So, so the interesting mechanical texture is because these are liquids with bits in it. So the bits, as you well know, can either be solid particles or polymer coils or surfactant aggregates. And so these aggregates or these bits confer a relaxation time on these different materials that is on the human scale, milliseconds to hours, hence interesting mechanical texture. So if you look at a modern introduction to soft matter that is written by Tom McLeish, this is soft matter, very short introduction. If any one of you want to introduce soft matter to a lay audience, buy the book. I don't have shares in the book, but it's a very good book. Have a look at his table of contents. How does he classify soft materials? The words he uses are words like milkiness, muddiness, inkiness, liminess, stickiness, jellification, soapiness, pearliness, liveliness. These are words on optical and mechanical texture. Pearliness is an optical texture. Muddiness is a mechanical texture. Jellification is mechanical texture. So in fact, it turns out, soft metaphysicist and a very well-known rheologist, when he writes about a subject, he classifies according to texture. And mechanical texture plays a very important part in the classification. Okay? So how were, in past tense, how were medical materials classified in the last 2,000 years? So in order to think about that, let's think about the structure of a recipe. So recipe, take thou, you, the singular, the person making recipe, you take some list of ingredients, A, B, C, inputs. You do PQR to them, you wash it, you put it in the mortar pestle, grind it up, or whatever. And then you make a medicine that will have certain effects. It cools the body or whatever. It's an emetic or whatever. Okay? Now, Galen, which all of you would have heard of, he died around about the year 200 Common Era, well-known Greek physician. He classified his medicines, his materia medica, his medical materials, according to their effects. You look at Galen's books, it tells you these are the medicines that actually make you vomit when you need to vomit. These are the medicines that cool the body. And then before him, Dioscorides, who died around about just before the turn of the 1st century, Common Era, he was not only a physician, but he was also a herbalist. And so the way he classified materials was according to input. You know, is it mineral, vegetable, or animal? If it is vegetable, is it a grass? Is it a flowering plant? See how he classified. It's a botanical classification. But what was new in the 16th century, people like Maranello and Calisteni, I'll come to Calisteni in a moment, is that they actually started to classify their materia medica by PQR. They classify their medical materials according to what they do to it and the texture of what comes out of it. 16th century is important because it is round about the 16th century that apothecaries decided that we don't want to be permanent under the thumbs of the physicians. They don't know what they're talking about when it comes to medicines. They only do the prescription. We have to make them. We have to give it to the patients, and if it doesn't work, the patient come and shout at us. So in fact, the first, the trade guild of apothecaries in Britain was given the royal charter in 1617. So, you know, a little bit after the 16th century, the early 17th century. So in fact, it turns out that this new way of classifying medicines was crucial to the self-understanding of that first generation of apothecaries who said to themselves, we want to be independent. We don't want to be under the thumbs of the physicians. So now let me take you to this text by Calisteni, which was published in 1562, I think also in Venice. But my Italian is not up to it. I'm assuming that maybe you guys are not up to it as well, except that our program chair, one of our program chairs, Emanuela Delgado. Hello, Emanuela. Waiting that you virtually, presumably you can tell me. But fortunately, my collaborator, Jill Burke, was fluent in Italian, If you tell me, look, syrups, various kinds of syrup, different kinds of infusions. This stuff is apparently a powder mixed with honey. You can lick syrups on sticks, quite often licorice sticks, preserved fruits, candied plants, aromatic sweets, powders, pills, tablets, various viscous eye drops, oils, and ointments with an increasing amounts of wax mixed in. This is neither classifying according to input, mineral, plant, or animal, nor is it classifying according to the effect on the patient, but actually this is classifying by processes and textures. How you make it, what does it feel like at the end? You see, that is totally different. And so this is neither the input nor the output, but is squarely in the mortar and pestle space. And in fact, when Jill, so I decided that Jill, my collaborator, needed to know a little bit of soft metaphysics. She's trying to teach me Italian, but I had an easier task, so I gave her Tom's book. She read this and said, but you know, this is copycat. I mean, if you switch to Latin, mutatis mutandis, the necessary changes haven't been made. This is identical. This is classifying things by texture and by processes. Okay, so she had a shock of recognition. So now I can see this, so across, you know, a few hundred years. So, I mean, Jill being an art historian, the next thing she did was, I mean, I wish she actually took me there, but we were doing this during the pandemic, so we couldn't go there. But there's a castle in Italy, the late 15th century fresco. It's a particularly fine example of this, but other paintings and woodcuts exist. Into an apothecary's shop. And in fact, this explained to you why rheology, why mechanical texture mattered to the apothecary as he was, or he in those days, as he emerged from under the shadow of the physician. It matters on how you make it. This is a mechanical rheometer with torque sensors in your muscles. It matters how you store it. I'll come back to that. And it matters to the client using it because it doesn't feel right on the skin and in the mouth. They come and shout it. So the rheology, the texture actually matters in the making, in the storing, and in the using. And at least two of these, in fact, I think storing matters too, is a matter of sensory properties. It's directly about how it feels like when you store it and how it feels like when you apply it on your skin or put it in the mouth. So let's zoom in. There are different kinds of storage equipment. These are glass jars with a wicker basket on the outside. And what they store are things like aqua violate, which is some kind of violet water. I don't know what makes it violet, but these are all aqua, something or other. Then there are these jars with a very fine spout. You can, I mean, the O tells you that in fact this is olive. This is various kinds of oils. And there are these jars, which are called albarello, the Italian name for them. They're open mouth jars. And they are for storing things that, I mean, that you may be able to see C's on here. This is a criotto, which is various kinds of balms. The word actually in modern Italian means plasters or band-aid. You know. So this is something that you put on the skin and you bandage it up. Various kinds of balms that you use for that purpose. And there are tablets of various kinds in boxes and also candy fruits in boxes. Now, why am I showing you this? Now think about it. So this is a fine example of an albarello from the London Wellcome collection of medical history. So this is for storing badger fat. These Italian words means badger fat. Don't ask what they use it for. But anyway, it was one of the things you could go and buy from the apothecary shop, some badger fat. Now think about it. Badger fat was what Bingham was writing about in this book. So this goes back to Bingham's original book on rigidity and plasticity. He invented the concept of, at least he popularized the concept of these plastic solids that has a yield stress of some kind. And that was a controversial concept, but I believe it. Okay, so these things have yield stress of some kind. And of course, they weren't stupid, these oil burner apothecaries. They know that if it has a yield stress, you need jars like this, not bottles like this, because you have to scoop it out. You can't tip it out, you have to scoop it out. Now, you might think that is obvious, but apparently that piece of knowledge was lost. I mean, the fact is, people make tomato ketchup, and tomato ketchup has yield stress. I looked it up. I tried it too. And people put tomato ketchups in bottles like that. So apparently that early modern piece of knowledge was lost, Mr. Hines. But they knew. And in fact, if you look through pictures, all the things with eustress are stored in bottles like this. Okay, so they knew. So what I'm saying to you is that this early modern apothecaries, they actually started thinking rheologically by mechanical textures. The way they classified their medicines, not according to input or output, but by the middle bit, actually is classified by rheological texture. And that turned out to have played an absolutely crucial role in professionalizing the apothecary's trade. So as I said, I think we should give them all retrospective early membership in the Society of Rheology. And that was the fun bit. There was, I know there's not an average Bingham lecture, but there you go, have some fun. I know you're waiting to the serious stuff with plots and stuff, but this is a serious bit, okay? This is the bit that may even have an equation with if you're lucky. Right, so this is a work that we have published fairly recently on rheological design of thickened alcohol-based hand rubs. And in fact, what this turned into, certainly for me, was a journey into ignorance. I happily thought that I could, in fact, do this, but in fact, the paper turns into an exposition of why we can't quite do this. So this is basically sketching our research program. That work itself was based on a review paper that the Edinburgh group wrote on what a bunch of soft metal scientists may be able to do to help respond to the COVID pandemic. Okay, so here's a graph of a review paper, two graphs of a review paper published in 2020. This is the Google search statistics for hand sanitizer and COVID-19. These are search statistics for hand sanitizer, pill, medicine, and drug, normalized so that this peak is 100 and this peak is 100. And you can see that about March 2020, the search for hand sanitizers just shot up. And that, of course, if you guys remember, everybody in the audience remember that far, that was the point when you go to the supermarket and to the drugstore, they all ran out. Okay, I remember I was at the pharmacist at the airport before a trip, before I went to the APS March meeting in Denver, that was cancelled, but never mind, only cancelled after I arrived. But there were hand gels to be bought at the airport there, and there were no hand gel to be bought at the airport when I came back. Okay, so there was worldwide shortage of hand gel, and certainly in Britain, what that led to during a lockdown was a lot of distilleries, especially small distilleries, with a whole lot of alcohol they couldn't use because there was a total shutdown of the economy. They started making hand sanitizers. So BrewDog is a particularly well-known brewer in the UK, and they brought out very quickly a series of punk sanitizers. Okay, and the recipe they use typically, I can't remember whether BrewDog actually used this, but typically when distilleries turn to make hand sanitizers, and also other people, when they turn to making hand sanitizers, they use the World Health Organization formulation, which is essentially an 80% by volume alcohol solution. Okay, and of course, I mean, you can go and do this. An 80% ethanol solution basically is twice the viscosity of water. It's Newtonian liquid. And that's not the hand sanitizer that you wanted to buy. And this matters because there was a paper a few years before the pandemic that actually shows that the hand feel of sanitizers, what it feels like to the user on the skin, actually matters for the clinical outcome. If it is too thin and people spill it, they don't sanitize their hands properly. If it feels rubbish, then people either stop using it or they use too little of it. They don't use it frequently enough. So there was very clear correlation between the psychorheology and the clinical outcome. And it matters not only for hand sanitizers, but also for other kinds of topical medicine. So this matters. Okay, and of course, the real trouble here is that the WHO formulation is a liquid, and what people are used to are gels. But you need much more specialized expertise to make gels than to make a liquid. And in particular, distilleries were not used to pumping fluids with yield stress. If you get it right, whiskey and gin does not have a yield stress, typically. Okay, so so they all started making this, and people don't like it. You might have experience of that, you know, they just all spill onto the floor. So then, and the reason, of course, is this is a Newtonian liquid, these are gels. And so the question is, as you try to formulate this into this, our group started asking, can we actually design ab initio from scratch a hand sanitizer with some kind of optimal psychorheology? That's what we hoped we were able to do. So this is how far we got. So, you know, of course, we take a standard Purell hand gel. We have to go out and, you know, try to nick it off someone because there were very few left to buy in the supermarket. I can't remember who actually got it, but we managed to find a bottle, maybe it was lying about. We measured it. So this is the WHO formulation. It's a Newtonian liquid, 2 millipascal per second. This is the Perel hand gel. It has a yield stress. And of course, the way you get from there today is using a polymeric thickener. So for example, the most popular one is carbopol, and there was in fact a worldwide shortage of carbopol at that stage. So these are cross-linked polyacrylate microgels. And of course, when you add water, the counter ions come out, the thing becomes charged and the thing swells. And that's how you thicken stuff. So if you work out, if you put your hands at 30 degrees to the vertical or 30 degrees from the horizontal, you ask what kind of shear stress does gravity put this bit of gel under. You very soon find out that at around 30 degrees, you need about order 10 pascals of yield stress to stop gravity yielding the gel. And you know, Perel is 10 or order 10 pascals, it works. And you might have spotted, of course, the assumption here is that it doesn't slip. Because it slipped, the entire lot slips off. I'll come back to that. So in fact, it turns out that you don't even need a yield stress. You just need to be viscous enough. I leave you to do the calculation. If you want a runoff time of something like significantly more than a second, but not as long as a minute, you only need a viscosity of 1 pascal second or so to get it remain in the hand long enough for you to rub it. So the first design criterion, that was the easy bit, that was the bit we could do, because there's no cycle in it. That's just pure rheology. I need a yield stress of order 10 pascals or low shear viscosity of 1 pascal second or so, but with no slip in the yield stress thing. But what are some of the desirable sensory properties? Now, to summarize it, the first thing, of course, is you want to minimize damage to the skin. Alcohol is not good for the skin. But then comes the rheological stuff. In the literature, there's a property called spreadability, which turns out to mean in literature, you read the literature, that you need to shear thin to something like 100 times the viscosity of water at something like 1,000 to 10,000 reciprocal second shear rate. You need to feel smooth, and it turns out that people claim that that needs a significant normal stress at about the same sort of shear rates. They need to be feel non-sticky, which some people call low spinability. It turns out that that means that you need low capillary breakup time. So you put it in capillary rheometer, the thread has to break up in less than about a second. That's chemistry. I claim total ignorance, so we cannot do that. We're doing it now, but not at that stage. This is rheology, so we thought we could do that. But it turns out that actually none of this is understood. These are all kind of semi-empirical correlations in the literature. So you measure Perel, you measure the standard carbopol. There's a carbopol Alchas turning. I'll come back to tell you what it is in 80% ethanol solution without any of the fancy stuff, which is essentially this stripped off all the perfume and all the rest of it. I'm not going to take you through in detail, but they take all the boxes, as you would expect, because they're hand gel cells. But let me tell you the bits that are perhaps understood in this table. Why 1,000 to 10,000 reciprocal second? Why that viscosity? Why that shear rate? It turns out that amazingly, that when we apply a topical formulation on our skin, we all instinctively stop rubbing when the film gets to about 20 microns. If you ask people who do this kind of research in industry, they know this. And the reason for that is as the lubrication film thins down, it is at about 20 microns that the deformed asperities start actually crushing into each other. Okay, so at 20 microns, you enter. This is a Stryback curve, friction coefficient against the inverse rate of rubbing if you on the thickness of the film. And when you get to about 20 microns, the friction coefficient shoots up. Okay, and when you work out 1 to 10 centimeter per second rubbing at 20 microns, you get this the shear rate. So there's a good reason why actually that's the shear end point. So I think that bit is more or less understood. We stop rubbing when the asperities on my fingers and the asperities on the skin actually start crashing into each other. I'm not going to go through this part because I'm running out of time, but this is by extension of rheology. But look, going back to my gel needing a certain amount of yield stress, that yield stress only works if the thing is non-slip. Yeah, because you need to stick to my hand, and then your gravity can just yield the rest of the gel. Fine. I worked that somehow. We need about 10 pascal yield stress. But if the thing slips on your skin, well, I mean, never mind yield stress, the whole lot slips off. And then you're left with no gel on your skin. So here's data from smooth cone plate. At 0% ethanol, Here's stress against shear rate. I'm going to take the derivative of this to show you that there's this little bit in the middle. This is classic sign of slip. So when I show you graphs like this is stress against shear rate. This is the flow curve, but this is the derivative of the flow curve. So this bit shows little p. It slips. You can do a classic carpal pull. I'll tell you the difference in just a second, which is called carpal pull 974. It also slips. It turns out the difference is this classic carpal pull is hydrophilic. This, according to companies, has been hydrophobized, turning into somewhat more hydrophobic. But both of them slips at 0% ethanol in a smooth cone plate. Now, we think we understand why Clarter and Ornakes and Mika published a nice paper back in 2004 telling us that in these hydrogels there's repulsive interaction between hydrogel and the surface. And so when you press the gel particle down, it deforms, it traps a lubrication layer, and the electrohydrodynamic interaction here gives rise to slip. That's understood. You can read that paper. However, when we added 80% ethanol, magically, in neither cases any slip, and there may be a very tiny bit, but basically there's no slip. This is just lucky because you need your hand gel not to slip for the gel to be worth, making a gel out of it. So that's interesting. Why is that? But again, the same group, a different postdoc, wrote another paper a little bit later. They explained that when the gel particle is charged, then there's the repulsive interaction with the surface, so it slips like the past paper. But if you get rid of the charges, get rid of the repulsion, it turns into attraction, then in fact things sticks. That's a summary of some of the things that they found out. So water has a high dielectric constant in ethanol. So that is the right direction. Lower dielectric constant would encourage the counter ions to condense back. And so if anything, you would predict that as you add enough ethanol, it would in fact, the counter ions would condense back. There's no repulsion, it will slip. Oh, sorry, it will stick. So that's the right direction. We find that when you add 80% of ethanol, neither of those two particles slipped. That means we are happy we can explain this. However, interestingly, if you are, suppose I gradually add alcohol, what happens? Okay. And in this case, in the classical carpal pull, which is hydrophilic, when you add ethanol, when you get to about 20%, the slip suddenly goes away. When you get to between 20 and 40%, it suddenly stops slipping. However, in the hydrophobized case, the slip is gradually turned on. So this is very nice data obtained by Andrea and a summer student this last summer. We don't understand it fully yet, but this is quite interesting. That in one case, the slip is abruptly comes off when you add enough alcohol. In the other case, the slip gradually goes away. Okay, so of course, always the most informative experiments are the simplest one that you do last. So towards the end of the summer project, we actually measure the optical properties. This is an optical texture. So if you go for the hydrophilic one, this is the transmittance over a range of wavelengths. What you find is that when you add alcohol to transmit it, this gel gradually becomes turbid. However, the hydrophobized one remains completely clear until you get to 85%, in which case the whole lot precipitates out and the thing turns turbid. Think about what that's telling you. Microgels is very low density polymers. The only way this could happen is in the hydrophilic case, as I changed outside from water to water alcohol mixtures, blue mixing with some red. I think in the hydrophilic case, the water alcohol mixture does not penetrate. The inside remains water. So the refractive index contrast increases and the thing becomes turbid. But I think in the hydrophobized case, in fact, the solvent penetrates. The inside is always the same composition as the outside, remains completely clear until the inside is so much alcohol that the chain just collapses or the charge condenses. That's what we think. However, why in this case counter ions seem to condense very suddenly at about 20–30%, and in this case it's gradual, we don't understand yet. I have some speculations. Anyway, so that was a serious bit. It was a fun bit. It was a serious bit. Here's my summary and conclusions. So I would make the case that those 16th century Italian apothecaries should actually be given retrospective membership SOR. They were the first people to actually classify their medicines according to rheology. And that helped them become an independent profession. So I think they were the first rheologists. I would make the case that psychorheology is actually a major frontier waiting to be explored systematically. Our work has exposed how much ignorance there is, certainly to me. And actually, I would claim that if what I said right at the end was right, then hydrogels and alcohol may actually involve some very interesting electrostatics, which can actually lead off to some very interesting rheology. But that's everything I've got to say. Thank you very much.